In this video, we're going to take a look at another example where we're going to be doing some nonlinear optimization, and it comes also from the world of finance, similar to our previous video on index funds. And so in this case, we're looking at the Markowitz mean variance portfolio model. So it's a little bit different than the index fund. So in the index fund, we were trying to build a portfolio that basically closely matched some market index. This is not quite the case. We're basically now trying to build a portfolio which strikes some sort of balance between risk and return, right? Typically, the bigger return also requires a certain amount of risk tied to it there. And there's always this weighing back and forth of how much risk you want to expose yourself to in order to gain a certain level of return. And so the Markowitz model basically measures return as the expected return. And so think of this as kind of the expected value from your probability background if you have one. And so you're thinking of a set of possible year scenarios in this case, each of them having a certain return, that'll be our R sub S, and each one of these year scenarios has a certain probability of occurring, and so that'll be our P sub S. And then in order to figure out the expected value or expected return here, you would then do essentially a sum product of the return values and applying that to the probabilities, and that's what this summation is showing here. And then risk will be modeled using the variance. And so here's your variance calculation here. Again, very similar. You've got the square difference between the year return and the mean, or excuse me, the expected return up here, and then you have that multiplied by the probability of that year candidate. So this is very similar to our index fund where you've got multiple years and they are assuming to be candidate years for what's going to happen in the next year. And there are also variations on this Markowitz model as far as how to actually formulate it. In one sense, you could say, I want to have a certain level of return and set that as a constraint and then minimize the variance on top of that. Or you could say, I want to maximize the return by setting a condition on the variance as well there to keep that in check. And so with that being said, let's go ahead and look at a more tangible example. So in this case, I'll just kind of talk through the Python code again, and then we'll see it implemented live in Excel. And so first, we're going to grab problem 17 from the course textbook. It has mutual funds as the investment options. It looks like there's 1, 2, 3, 4, 5, 6 mutual funds here, and there are 5 year returns that we're looking at. So we're seeing this nice body of this table showing up here. And the problem is formulated such that we're trying to maximize the return subject to some constraint on the variance, and that constraint on the variance is that we want the variance to be no greater than 30. Also, we need to know a little bit of information about the probability of each one of these year returns occurring in the next year, and you can see here they're saying that it is equally likely. So in this case, we've got 1, 2, 3, 4, 5 year returns. If they're all equally likely, each one of them has a probability of 1/5 or 20%. And so for the Python side, again, I'm thinking of it in similar methods the way we did the more generalized views of our linear programming problems, where like you can think of chapter 6 where we started talking about things in terms of sets and parameters, so on and so forth. So the sets that we have here looks like would be the investment options. That would be one set of things that we'd have to consider, and then another set would be these year returns here on the top level as well. And so we would need to define nomenclature for each one of those. You can see we're using S for the set of year returns, so it'd be like S1, 2, 3, 4, and 5, and I for the set of investment options. So like foreign stock, maybe take I1, intermediate term bond I2, so on and so forth there. And so then we need the parameters. So we've got some data tied to these things. One would be the probabilities of each one of those year returns. The other would be the actual returns on each candidate year for the different investment options. And so we would develop those out. In this case, I'm using the variable A for the numeric values you see in this table at the top, where it has two indices, right? One would be the year return that I'm talking about, and the second would be the investment options. You can see they're kind of two-dimensional in nature. And the other would be just the probability of some scenario occurring. So that just has one indice, right? That's the probability of year 1, 2, 3, 4, and 5. And in this case, it just happens to be a constant, but it wouldn't have to be a constant in reality. Decision variables would be talking about how much we invest in each of our mutual funds there. So 1, 2, 3, 4, 5, 6 here. So we assume that we have some level of capital that we're looking to invest, and then we are distributing that capital across my 6 investment fund options there. And now for the model, we need to incorporate obviously these elements here at the top. And so one of the things that our problem statement said is we want to maximize the return subject to some constraint on the variance. So if we set this R bar as our return, we could just say that we want to maximize R bar, and then we would define R bar as an equality in our constraints. And I believe that's what I've got down here. Yes, maximize R bar, and then the second in line here is the definition for what R bar is, the summation of all of the year candidates, and we're taking the product and that sum of the probability of that year candidate occurring times the scenario return. But of course we have to compute what the scenario return is, so that's what's right above it. Notice for every year in my year scenarios, I'm taking the product of the investment amount toward that investment option to the year return in that investment option, and summing all those up as well. So this defines R best, and I use R best in the R bar there. The third one here is fairly straightforward, right? If I'm having fractional bits of investment and I want to invest the entire amount that I have, all those fractional bits have to sum up to 1 or 100%. And then the last one, this is the statement on variance that was the other half kind of our Markowitz model. We're trying to, in this case, maximize expected return subject to a maximum allowable variance. And so in the problem statement before, it wanted to cap that at 30. And so we have the definition for the variance on the left hand side and just saying that's got to be less than or equal to 30, and then of course our non-negativity requirements for the investment options. So hopefully that all makes sense. As far as the actual implementation in Python is reasonably straightforward. I've got a pandas data frame here to hold all of the logic that I've just hard coded in this cell, and then I come down here. Basically this statement here is going to be dropping the mutual fund column and then just having all the numeric values and fund values. Here I'm figuring out how many funds as well as how many years, depending on the shape of this data frame. Then we are going to end up using this minimize function from the SciPy package. So I need to have, instead of just expected rate of return, I'd have the negative of that. And so that's what this function in Python is doing. We also are going to have a function that describes the variance. So this is just a computation of that variance expression here in that function. And then we need some constraints here. One is a linear constraint for unity. Basically just saying all the investment options are summing to 1. Remember these linear constraints, you basically pass it in as arguments the array that's kind of the coefficients for your body of your expression. In this case, we have just ones, so you can use the np.ones method to create a numpy array all full of ones, and the shape will be the same size as the number of funds themselves. And we're saying this is equal to 1, so then we would set the lower bound and upper bounds at 1 each. And so that works fine for the unity constraints. I'm sliding up here to this one here, but we also need to have this maximum allowed variance constraint in here. And if I look at this, I've got a squared term in here, and the R sub s is going to have my decision variables there. So we're going to have some nonlinearity in this one. So we wouldn't want to use the linear constraint, but instead we'd want to use SciPy's nonlinear constraint function. And so if I look at this, when I develop a nonlinear constraint, it wants a function which defines the constraint, and then we have bounds, the lower bound and the upper bound associated with it. And so if I look at this, I've already defined a function for the variance, and so now I just need to pass that into my nonlinear constraint and say the bounds are between 0 and 30. Then I've got some global bounds for my minimize function to work with, in this case just making sure it's non-negative, and then I need to pass in what we were trying to minimize, the negative of the expected return. I'm giving it an initial guess, so to speak, and so here I'm just basically guessing the initial position is the equal distribution of funds across all of my investment options. I'm picking a certain solver here, and then I'm listing constraints and the bounds there. After that, I am printing off the results and then just looping through all the candidate returns to see what the individual returns would be like, and as well as looking through the investment options here and doing a little bit of looping there as well. So in the end, we'd basically have an optimal solution where this would be the distribution of funds across the different options. So in this case, it looks like you'd have investments going to the foreign stock. The intermediate bond stock would be a heavy favorite at almost 50%, the large cap growth, as well as the small cap. Large cap value and small cap growth being neglected and not having any investments toward them. Then your returns for each possible candidate year is 19, 12, 5, 10, and 4, which computes an expected return of 10.45. And notice the variance, we're hugging right on top of the variance threshold at that 30% there. Okay, so that's talking through all the Python code. How would you implement this in Excel? Well, it's definitely doable as well. And so I guess, let's see if I can, get this side by side maybe, like so. And so in previous videos, I'll go ahead and have the data in our workbook here, just to minimize the amount of typing that needs to be done. And then we can start actually putting together our model. And so in this case, the data is on the top half. This will be the model. And of course, the first thing we need to play with are decision variables. And so I can just copy this down here, and let's say these cells that I'm forming here, and gray will be the decision variables. Of course, the decision variables being the amount of investment that I need to allocate toward each one of these options. Next, let's go ahead and look at an objective function. And so I'm maximizing something here. In this case, I'm maximizing R bar, but I haven't defined R bar yet, so I'll just leave that blank at this point and kind of move on to my constraints. And so my constraints here, the scenario return, for every return, I believe I would have that possible, and so I'm just looking at the way I've defined these things. I've got my returns up here as horizontal rows, so let's go ahead and try that. So we can say returns here, and this should be, I guess, more specifically our scenario returns would be here. And what is that? It is the summation of xi over the return for that given year on that given option. And so we can look at this, and it appears we can use sum product here, because we're basically wanting to do a sum product of, for instance, on year one, all of these values and the investment options tied to them down here. And so I will just come down here and say sum product a few times. One here. And then actually I can drag this, can't I? If I lock these cells up, then I should be able to just slide this over to the right and get that effect. Alright, so that's good. The next thing I need to do is define the expected return, R bar. So if I kind of do it the way I've at least illustrated here, I could say my expected return is here. I'm going to have to use the probability of each return for a few different times, so I'm going to first do that one. Probability of returns. It's called probability of scenarios. Maybe do this instead. In this case, they're all equally likely, so I think I can use count A to determine how many years I have here. That's 5. And I want to invert that, so 1/5. So this is the constant P sub s that we've talked about at this point. And then where were we? We were at the expected return. So I'll just have it here. And so the expected return, now I'm looking at R bar here, is just what? P sub s times R sub s, and I'm summing them all up for every year scenario. So our R sub s's were essentially these right here. In this case, we can actually pull the P sub s outside of that summation, so it would really be this value times the sum of all of these. Again, I'm able to pull that P sub s out of the summation because it's a constant and independent of the year scenario that I'm looking at. So that's looking good. Then we've got a couple more down here with our investment unity and the max allowed variance. Those will fit more nicely into this usual pattern of the left-hand side, right-hand side, and some sort of comment. That's the table that we're used to making when we were doing all those linear problems. One was an equality, one's less than or equal to here. In this case, 1 is 1 and 1 is 30. And again, this is investment unity, and this is max allowed variance. The investment unity, we're just summing all of my decision variables here. And in the max allowed variance, let's see, we can still pull outside the probability of S. Again, I'm looking at this summation down here, so I can pull this out. And then for each time inside, I've got R sub s minus R bar squared. So, for instance, here I'd have R sub s, that's R sub 1, minus R bar, which is our expected return, squared. And then we would do that for each one of these years. So hopefully that's all making sense. We're just kind of following the formulation we have there in the Jupyter notebook. And once more here. There we go. Okay, so at this point I think I've done all the work on the worksheet in order to get everything into our model. And so now we go to the Developer tab and the Solver. We've seen this before. We've got to set the objective here. We are wanting to maximize it, so that's good. We want to change the cells here. And that is fine. And then we need to add some constraints. Let's just go one by one here. We've got an equality here that needs to be entered. And then R less than or equal for our variance limitation here. Very good. We want to make the unconstrained variables non-negative. Yes, we are still okay using the GRG nonlinear solver. That is good as well. And so in this case, if we look at it, yes, actually our nonlinearity is going to come from a constraint. I believe that all the other examples we've looked at so far, they were the objective function here. And so this is where that nonlinear aspect will come from. And so we should be good to go here. I'll go ahead and solve it. The objective function must be a formula. So let's go ahead and close this. And I think I forgot to come back and reference this. Yes, I did. So this needs to equal the expected return. There we go. Let's try that once more. C27 is there. C18 to C23, yes, that's all good. Let's hit that once more. Alright, very good. The solver did find a solution. That's great. So let's just hit OK and keep it. Here are the different variations, and I think that's very similar to what we had before. Yes, 13, 50, 7, and 30 down there. Very good. So it looks like we have pretty good agreement between the Excel solver as well as SciPy's solver as well. 10.45 for the expected return and 30 on the variance. Yep. So these are looking good, and hopefully that helps you understand how to both formulate the Markowitz model as well as implement it in either Python with the SciPy package or Excel using its solver there.